Let us look at current voltage characteristics of the NMOS at DC or low frequencies. The study of circuits at higher frequencies will come later on. Look at this figure. This is the circuit symbol for an NMOS with the body terminal shorted to the source. Notice the double line with gate. This is to denote insulation from the device. Also notice the arrow here. This is to show direction of current. Although the device is symmetrical, the source and drain are distinguished by the fact that for an NMOS, the drain is always positive relative to the source. This is the circuit symbol for the P-channel enhancement type Mosfet. Notice the location of the source and the drain and see where the arrow is placed. Consider this conceptual circuit now. This can be used to measure the IDVDS characteristics of the circuit, a family of curves, each measured at a constant VGS. Look at this. We are familiar with the shape of the curves. We also know that there are two distinct regions shown here, triode and saturation. However, a third region also exists. Look at this. This is the cutoff region when the Mosfet is off. So now we have three regions, cutoff, triode and saturation. The saturation region is used when the device is to be used as an amplifier. Cutoff and triode are used when it is to be employed as a switch. So under what conditions will the device have to be operated to enter these regions? The device is cut off when VGS is lesser than VT. To operate the Mosfet in the triode region, we must first induce a channel. The VDS needs to be small enough so that the channel remains continuous. Remember that channel depth decreases with increase in VDS. So, this is done by making VGD greater than VT. This ensures a smooth, continuous channel. Now this can also be written as VGS minus VDS is greater than VT, which can be rearranged as VDS is less than VGS minus VT. Either of these conditions ensure that the Mosfet operates in the triode region. The current equation in the triode is on your screen. However, if VDS is sufficiently small near the origin, this point here, then we can neglect this squared term in ID. And we can write ID as this equation. Now this current voltage relationship represents the Mosfet's operation near the origin where the characteristic curve is almost a straight line. Hence we can write RDS as this equation with the assumption that VDS is small and the instantaneous VGS is given by VGS with a capital V, which is a DC value. RDS can also be written in terms of the gate to source overdrive voltage as this equation. Now to operate the Mosfet in the saturation region, again a channel must be induced. Now VDS has to be increased so much that the channel is pinched off at the drain. We achieve it by this condition: VGD is lesser than or equal to VT. In terms of VDS, this can be written as VDS is greater than or equal to VGS minus VT. The boundary between the triode and the saturation region, which you can see as the dotted blue line on the top right of your screen, has a condition which can be given by VDS equals VGS minus VT. If you substitute this equation into the equation of the current in the triode region, you will get something like this equation. This again proves what we had discussed in the previous lesson, that The current in the saturation region is independent of VDS. It does not appear in the equation. I hope you are comfortable with how to move from one region to the other in the Mosfet operation. Now to briefly go over the characteristics of the PMOS. To induce a channel, VGS should be less than or equal to VT. To operate in the triode region, VDS should be greater than or equal to VGS minus VT. For current in the triode region, the equation is same except that K-N is replaced by K-P. Now VT for PMOS is always negative, and VGS and VDS are also negative. Now to operate in saturation, VDS must satisfy this relationship. VDS is less than or equal to VGS minus VT. The equation for the current ID is again the same, with K-N replaced with K-P. Again, VGS and VT are both negative.